In this video, we're going to look at a classic problem in nuclear physics, the closest approach to the nucleus. So here is an alpha particle with 5 MeV of energy traveling to the right towards a gold nucleus. Calculate the distance of the closest approach of the alpha particle to the nucleus. And then part B, is this the radius of the atom? Pause the video now and try this question. So we need to understand what's going on in this situation. The alpha particle has some kinetic energy, and as it travels this way, it's being repelled by the nucleus, and the kinetic energy of the alpha particle is being transferred to potential energy. And at some point, which we will label x, at some distance from the nucleus, it will be balanced. All of this kinetic energy will have been balanced by this potential energy at this point. So what we need to do is we need to write down our expression for electrical potential from a point charge, which is V is Q over 4 pi epsilon naught R, where R is this radius here. Q is the charge on the gold nucleus. So what is the charge? Well, there are 79 protons in gold, so it's going to be 79 times 1.6 times 10 to the minus 19, because that's the charge on one proton. Now we need to firstly rearrange this for radius, so that's Q over 4 pi epsilon naught V. Now we need an expression for V, the potential. Well, we can write that down. We can say that EP is QV, or potential is energy per charge. So this is the energy that's going to come from the alpha particle. So let's rearrange that for V, EP over Q. And let's substitute this into that equation. So that means that we're going to have the radius is Q over 4 pi epsilon naught little q over EP. So what is this EP? Well, we've already said that the kinetic energy is going into the potential energy. This has 5 MeV of energy, so that's 5.0 times 10 to the 6 times by our conversion factor, 1.6 times 10 to the minus 19, which gives us an energy of 8.0 times 10 to the minus 13 joules. So now we can substitute all our numbers into this. So we've got our charge on the gold nucleus. We've got our charge on the alpha particle. So there's 2 protons in an alpha particle because it's a helium nucleus, over 4 pi epsilon naught, which is 8.85 times 10 to the minus 12, times by our energy, 8.0 times 10 to the minus 13 joules. Let's type that into our calculator. And we get our radius of 4.5 times 10 to the minus 14 meters. Is this the true radius of the atom? The answer is no. It's an upper estimate. Why is it an upper estimate? Well, because the EP, the potential, is obviously proportional to 1 over R. 1 over R squared. No, sorry, 1 over R. So as R approaches 0, the potential obviously approaches 0. So there's no way that an alpha particle is going to have enough energy to actually get to this point here. It's always going to be stopped somewhere short. So it's an overestimate or an upper estimate of the radius of an atom.